Okay, so talking about chapter 9, the second half on Mercury. The first half of this lecture and chapter covered the moon. And if we look at the characteristics of Mercury, we have our description here, comparing it to Earth with its size, its density, orbital period, semi-major axis. So that's going to be like its distance from the sun. This relates to how much hotter it is, how much more intense the sunlight is at Mercury's location. Its rotation period, which is how long it takes to spin on its own axis, and its orbital tilt. These are the same characteristics that we see for each of our planets. So these same ones we saw for Earth, exactly formatted like this for comparison. Dense planet, second densest planet in the solar system, Earth being the densest. Quite small, if in terms of its radius, certainly in terms of its mass. The more dramatic difference in mass is due to the fact that mass proportional to volume, right? And volume is related to the cube of radius. So that's why you always see such a big difference in mass, even when the difference in radius is, doesn't seem as large, right? So if you wanted to make a good estimate, you'd say that Mercury is about 40% as wide, or its radius is 40% as large as the Earth's. The other next noteworthy thing, before I get to the most noteworthy thing, is the orbital tilt, which is 0. So it is just not tilted at all, which we'll see is there's all kinds of tilts in the solar system, so there's not like a clear trend. But in comparison to Earth, it's a big difference, right? Because we have 23.5. I did mention that the semi-major axis is all about intensity of sunlight, because it's, how far are you away from the sun? And almost with the same ratio as its size is its distance from the sun. So 0.39 AU, remember that AU are astronomical units. An astronomical unit is 1.49 times 10 to the 8 meters. So that works out to be, well, actually kilometers, 1.49 times 10 to the 8 kilometers, because it's 149 million kilometers. In meters, it would be, well, 3 more zeros. And besides the, that value, this noting here that it's 40% of, our distance from the sun means it's much closer, right? So you could say that it's over, twice as close to the sun, right? Or its distance from the sun is less than 1/2 of our distance from the sun, ours being Earth's. Does that mean it's a whole lot hotter? Well, yeah, because the effects of the heat from any heat source, the sun being no exception, is not just going to go directly with distance, but instead with the square of distance. So if you're twice as close to a campfire, for example, heat source, right? Kind of acting like a, like a sun in that case, if you're surrounded by cold surroundings and that's your, one source of heat, then if you're twice as close to that campfire, you're going to be 4 times as hot. So that's the way that it works, the way that the mathematical relationship works. So we expect, Mercury to be quite a bit hotter. Having the sunlight be 4 times as intense would make a big difference. And indeed it does. We have some very hot days on Mercury. And what can we say about its days? Okay, well, it has very strange days. And that's because of the fact that its rotation takes 60 days to complete. But its year, well, it's 58, okay? You'll notice that I really round in the case of Mercury, because there's a ratio, there's a nice fraction that comes out of rounding. So I'm in the habit of doing it. I wouldn't be for, other cases necessarily, other, rotation periods, but 58 days, okay? So we're going to round that to 60. From now on, I'm really going to refer to it as 60 days. Its orbital period is 88 days. By days, we mean Earth days. And this is just like a unit of time, right? And also so we can compare to our own day. Obviously, 58 days means that it turns really slowly, so it's real sluggish in its rotation. And rotation is like this, the red arrow, right? It's the rotation around its own axis. Okay, so what's most interesting though, besides being, real slow and having an incredibly long day, right? Because you think about that means about 30 days of, facing one way, 30 days facing the other. If this was a orbit that was much longer, then we could kind of say that this would be like 30 days of sunlight and 30 days of darkness. And for comparison, think about the moon. Okay, so the moon has that rotation period that is 28 Earth days, and that's equivalent to its orbital period around Earth. So that means when you're on the moon, you're going to have, a little bit more than 28, but let's, getting round. You're going to have about 14 hours of sunlight. Sorry, 14 days of sunlight. So this really long lunar day. So the lunar day just lasts and lasts and lasts, 14 Earth days. Eventually, the sun's going to set, whatever your location on the moon is, and then it's going to be 14 Earth days of darkness until the sun rises again. So you have this really long pattern, and it really is steady like that. You can just, directly say, hey, you got this really slow rotation, and it just results in that relationship. But with Mercury, it ends up being not that simple, because the reason that that works for the moon, and we can just take that long rotation period of almost 30 days and just cut it in two to find out how many days there are of sunlight and how many days of darkness, is because the moon is orbiting Earth, and Earth orbits the sun with a orbital period of 365.25 days. Okay, there's no rounding there because, again, out of habit. Now, that means that the orbital period is much longer than the rotation period. So we don't have to worry about how the two interact. But when there isn't a really significant difference, right? Because there's over a factor of 10 in that case. Take 30, multiply it by 10, you don't have 365 yet. But here, I mean, what's the difference, right? The rotation period is 2/3 of the orbital period. When the values are that close, well, you have to be a lot more meticulous and a lot more discerning about how these two periods affect each other. Okay, so Mercury completes, and it's continuing the same thought, 3 spins in every 2 orbits. Okay, as we saw, 3 spins in every 2 orbits, because 3 times 60 is 180, 2 times 90 is 180. That's where that comes from. See, spin 59 days, orbit 88 days. Once you estimate them, you have this, that statement. Okay. All right. So I'm going to switch this video, but you'll see it in just a moment. Almost there. All right. All right. Okay, I'm going to restart this a few times. So, okay. And I kind of, I can advance, but not the rate I want to. So. Okay, I just adjusted the playback speed if you wondered what I was up to. Okay, so there we go. All right. This animation is going to be showing us Mercury's orbit around the sun. And obviously this idea is important, which is why I'm spending a few minutes on it. To quickly point out, there are some axes, but they don't concern us other than that they represent space, distance. This is just like a bird's eye view of, looking down on the orbit of Mercury around the sun. Values don't matter. They're essentially just scaled. The orbit is shown as elliptical fairly accurately. Mercury does have, interesting fact, and often brought up, the most elliptical orbit of the 8 major planets. Okay, because Mercury, absolutely, despite being fairly small, is a full-size planet, proper major planet, and its orbit is fairly elliptical. Not dramatically so like a comet's, but fairly elliptical and much more than any other planets. Okay, so now let's go ahead and start play with one last note that this little black dot represents the point of view of an observer on the surface of Mercury. So essentially, this is you, right? You're standing on the surface of Mercury. In just a moment, one of the last things that we'll point out is that this is would be very difficult to do because you'd probably melt. But let's assume you have some very sophisticated survival, station of some sort, and you're underground, but you got some thick glass, and you're looking up towards the sun, and you see that it is noon, right? Because the sun is in your local sky at its highest altitude. All right. And if you were at Mercury's equator, the sun would be at your local zenith. But wherever you are, whatever latitude on Mercury, the sun would be as high as it's going to get in the sky, and it's therefore noon. And now we're going to start the clock. Okay. So we're now orbiting Mercury, but also the planet is rotating. But notice that it's rotating very slowly because we know that, right? The rotation period is 2/3 as long as the orbital period. It's almost so far looking like a tidal lock. A tidal lock is what the moon has with Earth, where one face always faces the orbited body, the larger body. We can tell that it's not quite a tidal lock already at this stage in its orbit because we're kind of starting to lag behind. If Mercury was truly tidally locked to the sun, then this black dot would be still pointing directly towards the sun. And the two rates, the rotation rate and the orbital rate, would be exactly equal. And that would allow the black dot to just continually face the sun, which means there'd be one side of Mercury that faces the sun and one that doesn't. If a planet was tidally locked to a star, then you would have truly a dark side and a light side. You'd have one side of that planet that just continually gets sunlight and one side that never does. We don't have any tidally locked planets around our sun. It does seem to be a feature of planets around other stars, by the way, kind of interesting to think about. It's a real thing, but it does not exist in our solar system. All right, so now we can clearly see, okay, so it's not tidally locked, right? That rotation rate is slower. So that means that we're kind of lagging behind a bit. And so we get to this point, and I just want to point out where we get right here, which is half a orbital period and so that's 45 days. So it's 3/4 of a rotation period. So half an orbital period, but 3/4 of a rotation, the sun is set. We went from noon to sunset. We can tell it's sunset because, our black dot, which is us as the observer, has the sun at 90 degrees to our zenith direction, which means the sun would be setting at the horizon. And now we're entering our night. So here we are. Now we're in Mercury night. Obviously, other people on Mercury wouldn't be, but at our location on Mercury, we're now into the night. And the nighttime is continuing. Continues right around all the way back to where we started. Quickly pause again. So now we've finished one complete orbit. We've also finished a rotation and a third. And we're at a point now where the time of day in the solar sense is midnight. We're facing exactly away from the sun. So this is the middle of the night for us. So that means that after one full orbit around the sun, we don't get back to where we started. See, because we're not back to, we haven't repeated our orientation. This black dot isn't facing the sun as it was when we first began.
Mr. Trevor, excuse me for interrupting. I don't know that most of us can see what you're seeing. It's not moving on my end at all.
Oh, wow. Oh, that's unfortunate. Can you see
Okay.
it, can you see it now?
Yes, now it is. Yes. Thank
Okay.
you.
And now is it moving?
Nah, no, it's stopped right now.
Ah, shoot. Okay. Okay. Interesting. So when I enter full screen, it doesn't show up. Okay. All right. So that's unfortunate. I'll try to just not say everything again, but at least point out that this is one of the stages I was talking about a moment
Uh,
ago,
Thank you.
where you had this was sunset. So sunset occurred after half an orbit and 3/4 of a rotation. And then we'll just start. This is, near the beginning. And this is when I was pointing out that we could see that with that rotation rate being 2/3 as long as the orbital rate, we're lagging behind. We're not just, staying directly facing the sun. So we reach this coming up on this stage, having started at noon. Now we hit sunset of our Mercury solar day. And now we're into nighttime because that black dot's facing away from the sun. So it would be night at our location on Mercury. And then what I was just saying was that once we get to this point, which we'll be into in just a minute, we'll have completed a full orbit. That's a Mercury year, right? Because an orbit is a year. That term, means a year. And so, a complete orbit, it is synonymous with a year. That's what, not an Earth year, right? That's just unit of time, but that's what it represents. Okay. And specifically, it would be in this case, to go all the way around and get back to where you started, that's a solar year. Okay. Now, what, are we back to the same time of day? Because certainly with Earth, right? If you get back to that, after 365 days, then you can say, okay, well, then you can, have noon on that day and you can get back to that exact same orientation because the days are so much shorter than the year. But here, it's clearly not the case. After one full year, we're not back to the same time of the day, and we can't just, say that, okay, we're going to, have the planet spin and move insignificantly in its orbit, because that won't be the case. So how long will it take to actually get back to where we started? In what I mean by started, it means like both the same position in the orbit and the same orientation in the rotation. So we need to get back to the same point so that the black dot is where it started, and or rather the red dot, and also the black dot is facing in the same direction we started. So if we want to have a complete cycle, we need to get back to this. Black dot facing the sun, red dot at that starting point in the orbit. So after one orbit, we are definitely not there. In fact, it's the exact opposite time of day. We started at noon, now we're at midnight. Midnight because we're facing directly away from the sun. Black dot's on the far side. So we continue with this process. We're going to keep going around the sun. It's still nighttime. So what's interesting is that our Mercury night, if you remember, started after half an orbit. Now we're almost a full orbit around, and the sun still hasn't rose. And look where it's going to rise. Right there. So that means that night lasted one orbit. You see, because it started right when we were at the same position, when the red dot was at the same position, and we had to go all the way back around, and then we continue. Now we are at, the sun is rising, and now we're in our morning on Mercury. And as you can probably see, we are now approaching that key point when the cycle will be done. The video continues for one other complete cycle, but we'll stop it here. We're going to get back to noon and return to that same position. So what does that tell us? What it tells us is, and I'll switch back to slides, that the relationship between the Mercury day and Mercury orbit is such that, and because of this 3 spins to every 2 orbits, is such that it takes 2 Mercury years to have 1 Mercury day. In other words, a day on Mercury is 2 years long. And by a day, what do I mean? A solar day. Just a full cycle of sun rising and setting. What do I mean by a year? I mean an orbit. Okay? To put that in the Earth days, it takes 180 Earth days, approximately, right? Rounding 88 to 90, which means 2 full orbits to complete a solar cycle. A solar cycle is a solar day. To refer to terms we saw before, terms about the difference between sidereal days and solar days. The sidereal day is the spin. So you could say the sidereal day of Mercury is 59 days or approximately 60. The solar day, which is the more natural, intuitive type of day, right? So when you notice, is 180 approximately. Okay, 180 days. So it's 3 times longer than the sidereal day and twice as long as the year. And that, I think, is pretty cool. Hopefully you agree. It's a neat little thing to work out, to reason out, to see how it can work, despite it being so strange and initially counterintuitive, which makes it all the more interesting and gratifying. Right. And we really kind of covered a lot of key things, right? The slow rotation. We've already mentioned the elliptical orbit. I want to just quickly touch base on the temperature. And then on a lot of the remaining slides talk about where you'll see the content elsewhere. And what the heck do I mean by that? Well, you'll know in just a moment. So Mercury, as I said, close to the sun, and it also with that really slow rotation, has extreme variations in temperature. Its highs are 430 degrees Celsius. Okay, this is like an oven, a hot oven at that. Its lows are negative 180 degrees Celsius. So incredibly big swings in temperature between its day and nighttime temperatures. Why? Well, first of all, being close to the sun, all right, but also having no significant atmosphere. It has a tiny amount of atmosphere created by dust. There's a number, one of the discussion questions gets into that, and it's content that you can see in the book. So there's like this very, very thin atmosphere. Despite this, there is likely some ice for the same reason, and I think the reason I want to bring this up is because it ties in nicely with what we learned about the importance of craters at certain latitudes, especially on worlds like both the moon and Mercury that have no axial tilt, because when you have that crater near the pole, you have no sunlight ever reaching the bottom of the crater. And that means that you can just have these conditions where that surface location, even if it's only a few square kilometers total, is going to be completely protected from the sun's energy. And you can have ice remain there for hundreds of millions or billions of years and retain primordial ice under conditions that would otherwise seem impossible. The composition is a lot more metal than other planets. So notice that this kind of cross section of the planet shows the core, much as we saw the core of Earth, and it's a lot bigger, you know? So like Mercury is a stone fruit with a really big core, right? I mean, more of a peach than an apricot, because it's got this really proportionally large core. And if you don't recall, go back and look at the slides for Earth, and you can see that the mantle, which is this region with sort of the salmon color, red color, is on Mercury rather thin, on Earth quite significant. The core is iron nickel, not unlike Earth. It does create a weak magnetic field, which is really kind of strange. We would expect Mercury to be fully cold and therefore not have any magnetic field. Mars, for example, is completely cooled. Its interior is not molten, and you have to have a molten interior in order to sustain a magnetic field. And Mercury, being even smaller than Mars, should have already had time to cool since it was made. But it hasn't. The best theories suggest that that's because of the composition of its interior that has just been cooling more slowly than other comparable planets. Okay? And the reason that we know it must be a liquid is because it has that magnetic field. It is impossible for a planet to have a magnetic field if its core, or just its interior really, is entirely solid. You have to still have liquid, which means molten, inside of a planet to sustain a magnetic field. Right? Despite that, it's safe to say, and despite what? Well, despite the molten core, it's safe to say that Mercury is geologically dead. Whatever leftover heat there is that keeps some of the interior still in a molten non-solid state, that heat is not sufficient to break up to the surface to create volcanic activity or any type of fissures, let alone plate tectonics. There just isn't enough heat to sustain any geological activity. Okay, so the lava flows that we do see on Mercury are ones that happened billions of years ago during the early stages of the planet. Mercury is heavily cratered because its surface has never been affected by significant amounts of volcanism, at least especially not in the last 2.5 billion years. Why does that matter? Because there's never been a chance to resurface the planet, right? There's no atmosphere, so there's no weathering. So all the craters that exist are going to be craters that have been around since the very beginning of the planet's differentiation and solidifying of its crust. Okay. There are a number of features. One that I want to mention are the scarps, which are large cliffs. They stretch hundreds of kilometers, and they actually represent a shrinking of Mercury. If you imagine something cooling like a pie when you take it out of the oven, and as it cools, it shrinks, and you can get wrinkling because of that shrinking. Well, that's what happened to Mercury as a planet. Okay. We see that with some moons, but it doesn't show up on other planets. I'll only say a word about Mercury. The fact that they kind of joke and say, "Oh, there is none," right? Nothing to talk about here. But then they get into it a bit about why there's not a significant atmosphere. And you might be thinking, didn't he just say that there is some atmosphere? The atmosphere that's created is sustained because of basically dust being vaporized by the incoming sunlight. So it's an atmosphere in the case that it's being continually created as the regolith on the surface, remember that term from the moon, is getting vaporized by particularly intense sunlight. And there you go. You've got some vapor, trace amounts of it. But it's only there because it's being continually created. Mercury is not able to hold on to any atmosphere in any way. And that's because of a combination of two factors. Okay. Where are you going to see these combinations of two factors, and why are we not going to talk about them just now? Well, you're going to see them in the homework, and that's where you'll have a chance to fully explore them, read the descriptions about what these two factors mean and why they can lead to the concept of atmospheric retention. The two, to summarize and to, preview what you may have already seen in the homework or otherwise will actually see, so an actual preview, is factor number one, the thermal speed. Thermal speed has to do with how hot your planet is and what molecule you're talking about, because we're talking about atmospheres here. And when we talk about atmospheres, we talk about which molecules compose that atmosphere. Recall when we talked about Earth, we talked about the different types, the primary, secondary, and current atmospheres, and the different molecules of each, right? On Earth, for example, nitrogen, right? In the form of molecular nitrogen, N2 was a key component, a key molecule. If you wanted to talk about the thermal speed of the, molecule of nitrogen, you would use this formula right here, which is, sorry, badly formatted, but perfectly, clearly formatted in the homework. And what you just need to know the temperature of the planet, because that temperature of the planet is going to be the gas temperature. So you equate the two. You say, hey, this is how hot the planet is, therefore this is how hot the gas is. Then you're able to find the average thermal speed of that gas. In other words, that's how fast it's bouncing around. You then relate that to the escape velocity, which has to do with gravity, because bigger planets take more velocity to escape. We talk about launching rockets into space. They need a certain amount of escape velocity. Well, if you want to worry about a molecule escaping into space, you need to know how fast it's going. So it's the combination of that thermal velocity and the escape velocity. This is the bit about gravity and escape velocity that allows you, here's the calculation, allows you to find out by comparing those two velocities, which is going to dominate, right? Is your thermal velocity greater than your escape velocity? Well, that means the gas can easily just, take off into space and it won't stick around. You can't build an atmosphere or something that can easily escape. On the other hand, if your thermal velocity is way below your escape velocity, then that gas will stick around and not easily escape into space, or practically never escape into space if the difference is sufficiently large. So that's the idea. I think you'll have a chance to explore it in the homework. All right, so that wraps up our discussion of Mercury. And then we can head right over to the quiz.